So there are valence electrons and there are core electrons. The valence electrons are important because they have a big effect on how an atom behaves. So what are the valence electrons? Valence electrons are those in the outermost principal energy level. In other words, they're anything where it has the highest N. The highest N, or in the hotel, the highest floor. So, do you have electrons on the third floor, but not on the fourth floor? The third floor, those are the valence electrons. If we look at the periodic table and look at the group numbers, 1A, 2A, 3A through 8A, that number corresponds to the number of valence electrons, which is why I like to use those numbers instead of the 13, 14, etc. Because for those, you have to knock the 1 off. But if we look at group 5A, with nitrogen and phosphorus, everything in that column has 5 valence electrons. You go all the way to the end, to the noble gases, except for helium, everybody has 8. Okay? So then we also have core electrons. Core electrons are the ones that are closer to the nucleus, closer to the front desk. Those are the ones in the lower floors. Any questions?
It's always 2, the core electrons?
It's not always 2. Yeah. It's a good question. So what we find is that elements in the same column, in the same family of the periodic table have similar chemical properties. That's why Mendeleev put them there. And the reason they have similar chemical properties is they have the same number of valence electrons. Right? So this is just showing electrons in the highest occupied level. So 1s1, this has 2s1, 3s1. So you go to the second group, and now beryllium's going to have 2 valence electrons. Magnesium's going to have 2 valence electrons. And you keep going across. Here's nitrogen. We said it's in group 5A. It's got 5 valence electrons. It has 2 electrons in the 1s, and then it's got 2s2, 2p3. So we're looking at 2 plus 3 is 5. But it just goes 1, 2, 3, 4, 5, 6, 7, 8 as you go across. Write an electron configuration for phosphorus, identify the valence electrons and the core electrons. I'm going to do an orbital diagram first, just because. It's 1s, 2s, 2p, 3s, 3p. And we're staying away from the part where they get all jumbled up. How many electrons does phosphorus have? 15. So I'm going to stick 15 electrons in here. 1, 2, 3, 4, 5. Take your own bed. 6, 7. Now you got to pair up. 8, 9, 10, 11, 12, 13, 14, 15. So once we have that, it's very easy to write the electron configuration. The 1s has 2 electrons. The 2s room, sublevel, has 2 electrons. 2p has 6 electrons. 3s has 2 electrons. And 3p has 3 electrons. So it says identify the valence electrons and the core electrons. The valence electrons are the ones with the largest number here. So 3 is the largest number. All of these are in the third energy level. All of these electrons are staying on the third floor of the hotel, right? So the valence electrons are the ones that if a tornado came and took off the top of the hotel, they'd be the ones that got taken away, just the top floor, okay? So those are the valence electrons. When we're looking at electron configuration, we're looking at, what's the highest number? We've got 1s and 2s and 3s. 3 is the highest number. So it's all of the 1s with a 3. So phosphorus has 5 valence electrons, and I often abbreviate those VE, valence electrons. So these would be the valence electrons in the orbital diagram. Yeah?
In situations where you have, is valence electrons just highest principal energy level, or just like highest energy level in general?
It's the highest principal energy level.
Okay, so if it was
So-
like the 4s and the 3d, it would be the 4s.
Yeah.
Okay.
Yep. Okay, so the periodic table. This is where there's some magic in the periodic table. So we can look at the periodic table and divide it into 4 blocks that represent filling the different quantum sublevels, S, P, D, and F. It's all hiding up there. The group number for main group elements tells us the number of valence electrons, and the row number, the period number, tells us what the highest principal quantum number is for any of the electrons in that atom. So here we have it. So this part represents the S block, and notice helium. He's over here. He. Why is he over there? Because he is not quite the twin, but almost as young as hydrogen. And so he just kind of breaks all the rules. In some ways, he should be over here because his electron configuration is 1s2. But in other ways, he belongs over here because, as we'll find, these guys all have a full valence shell. This guy also has a full valence shell, and that's what makes them particularly unreactive. So don't worry about helium. So how many columns are there here? 1, 2. How many electrons can fit in a S sublevel? 2. There's only 1 orbital. This represents the P block. The P sublevel has 3 orbitals. It can fit 6 electrons. 1, 2, 3, 4, 5, 6. The D block, the D sublevel has 5 orbitals. How many electrons can it hold? 10. Look at this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. F. How many orbitals in an F sublevel? 1, 3, 5, 7. 14. 14 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. What? So what is so amazing to me about this is Mendeleev put these things together based on their properties and atomic masses. He knew nothing about quantum mechanics. And so then quantum mechanics comes along and totally messes up physics and disturbs chemistry significantly as well. And we end up with this quantum mechanical model, and they came to that by solving these equations based on the electron behavior of hydrogen, and they end up with something that has this same 2, 6, 10, 14 business. That's pretty amazing to me. So to write an electron configuration, you just basically start with the first one, and you can count your way over. So hydrogen, helium, lithium, beryllium. So let's just say we're going to do carbon. So how would we write the electron configuration for carbon? Well, this is the 1s, and there's 2, 1, 2. So you've got that guy and this guy. So that's 1s, 2. And now we're in the second level. 2s, there's 2 electrons there. This is still in the second level, and we're just going over here, there's only 2 electrons. 2p6. Sorry. Just kidding. 2p2. Does it make sense? So I filled the 1s, and put 2 electrons each. Each element essentially is another electron filling in, right? So this is 2 electrons, and then here's another 2 electrons, and then here's another 2 electrons, a total of 6. If we kept going, if we went, 1, 2, 3, 4, if we went 5 electrons in this P, then that would be fluorine. And here, this is showing you essentially the valence electrons. So chlorine is 3s2, 3p5. Bromine is 4s2, 4p5. Iodine is 5s2, 5p5. You see the pattern there? 2 plus 5 is 7. All of those guys have 7 valence electrons. This is the best cheat sheet ever. So I kind of went over this on that one. Here, let's do a noble gas shorthand for chlorine. So here's chlorine, and if we're going to use the noble gas shorthand or the inner electron configuration, here's my chlorine. I go up and all the way to the end to find the previous noble gas. And so I write that guy down with brackets. That stands for the electron configuration of neon. And then I'm going to go past that, and here I am. This is the third level, and 1, 2. 1, 2. So 3s has 2 electrons. And then I'm getting over here, and I've got 1, 2, 3, 4, 5. The 3p has 5 electrons. Once you see it, and then it's easy. Okay, use the periodic table to determine the electron configuration of bismuth. Now, this periodic table doesn't have all the pretty colors on it. But there's parts that stick up, right? So that's the S part, and this is the P part, and D is in here. That's S, P, D, and F is down there. So bismuth. So did I write on bismuth? No, I didn't. Good. So here's bismuth. Should we do the full electron configuration or the noble gas shorthand? Noble gas shorthand. That's a lot of stuff to write down. So the previous noble gas from bismuth, I go up this to the previous row and go all the way to the end, right? That's the closest noble gas before bismuth. And so that is xenon. And then from here, I'm going to go and, well, of course my line here covers up the row numbers. If your periodic table doesn't have period numbers or row numbers on it, it's very easy to add them yourself. It just starts with 1, 2, 3, 4, 5, 6, 7. So we're looking at row 6, right? Because this is the end of row 5. So we're coming over here, row 6, and there's 2 blocks here, two elements there. So that's the S area. That was 6s2. Now we come to D. We haven't come across D before. In the energy ranging, there was some misordering, right? And so for these D ones, these are n minus 1. So the row number is the same as the principal energy number. So if we look at this row for the D block, that's in n equals 4. But doesn't this look like it kind of sank down? This is lower than it should be, it seems like. It's actually exactly where it's supposed to be. So I'm going to take the period number and subtract 1. So this is 3D, and this is 4D, and this is 5D. Okay? And then there's this fun little piece. There's this arrow here. There's kind of a gap there, and then it goes down here. And if you look at the numbers, right, 57, 72, what? 57, 58. So on the classroom wall, that's how the periodic table should be set up. And we did it that way because the other way doesn't fit up there. But I think they do it like this, usually, because it doesn't fit on a piece of paper very well. The aspect ratio is just not very good. So they pull these guys out. We don't use them much anyway. They pull those out and just stick them at the bottom. But the one on the wall is actually telling us how it's supposed to be. And so you see how when we go from 57 to 58, that looks like another section that is sunk down. So for F, we have n minus 2. Because this sank even one lower. So coming in here, this is going to be 6s, and we've got 1, 5d, and then it jumps over to these guys. So we're just going to ignore that guy for a minute, and we're going to come over to the F block. This is n minus 2. Well, n is 6. 6 minus 2 is 4. So this is 4d. How many electrons? Oh, I was using green. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. You don't actually have to count them if you remember it's 14, but if you don't remember it's 14, you can count them, right? Come back. Phew. Okay, I wrote D. I didn't mean to do that. That's F. So this is the 4F, and there's 14 electrons in there. So now we're going to come back and deal with these guys. We kind of just set that guy aside. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is n minus 1, so the row number minus 1. So this is 5. 5d, and there's 10 electrons in there. We get over here. This is part of the main group, right? And this is part of the main group, and the numbers are just the numbers for the main group. The transition metals, it's n minus 1, and these guys down here, it's n minus 2. So now we're into P, and this is the same as the row number, so this is 6P, 1, 2, 3. 6P3. Any questions? You see how I did that? What you need to do is you need to practice it and make some notes on your periodic table and do all the homework and stuff until it makes sense to you, right? Once it makes sense to you, you'll never forget it. So this is asking us to write electron configurations for each element. We'll do the noble gas shorthand. So for chlorine, find it on the periodic table. It's right here. And then for the noble gas shorthand, go up a row and to the end to find the noble gas, because that's going to represent all the core electrons, basically. And so then we're coming in at row 3, right? So this is S12. So that's 4S2. No, it isn't. That's 3. Because the arrow's pointing at the 3. So that's 3S2. And then 1, 2, 3, 4, 5. That's 3P with 5. Next one is silicon. Here's silicon. What noble gas are we going to use for silicon? We'll also use neon. So for silicon, we've got neon. And what comes after neon? 3s2. And then it jumps over to 3p. And how many electrons in there? 2. 3p, 2. Let's do strontium. Here's strontium. Well, what's the previous noble gas? Krypton. So we've got krypton. And then we're coming into row 5. 1, 2. S1s. 5, S2. And oxygen. Oxygen is up here. So it's a little silly, but we can use helium. He. And then we're coming here. So what is this? 2s2. And then 2p4. It's basically just counting off the position in the periodic table. It'd be nice if things all followed that order, but they don't. So that 4s sublevel is lower in energy than the 3d. So the 4s fills before the 3d, and that's what we saw in the periodic table. But the difference in energy between those two levels is very small. And so some of the transition metals don't follow the pattern. They have irregular electron configurations. And those have to be found experimentally. And there's only 2 of them that I want you to remember. And that's chromium. Well, that's the wrong one. Chromium and copper. So if we look at the valence, well, if we look at these guys, right, the stuff past the noble gas. So 3s2 and 3d4. The 3s is full, and the 3d has 4 out of 6 electrons. So 4s2 and 3d, 1, 2, 3, 4. Not 6 electrons, 10. But what it actually does is this 4s1, 3d5. This electron hops up here. The price difference between these rooms is really small. And so for like 5 cents extra a night, this guy can have his own bed. Well, I would do that. So he's gonna go up there. This is a special situation where we have this sublevel and this sublevel both half filled. There's like symmetry there. It's like a Groupon coupon. You know, you do these things and you get this thing off. How often can you actually, do all the things? But if you've got 2 half-filled rooms, you get a discount. So chromium actually does that. And if we look at what copper does, it's kind of similar. This is what we expect copper to be, with 9 electrons in the 3D level and 2 in the 4s level. But what happens is this electron over here comes over there. It's like, well, he didn't get his own bed. Why did he do that? Well, now we have this one that's completely full and that one that's half full. And people who like symmetry and order are like, well, yeah, that's better. Right? So chromium and copper do that. These ones are fair game on a test. The rest of these, molybdenum kind of does the same thing. Krypton, I don't know why he does that. And here this one is, the D is full and the S is empty. But you don't need to remember those.